Hello, everyone, and welcome to our very last afternoon of Astronomy Day programs with the North Carolina Museum of Natural Sciences. My name is Nancy, and I'm going to be hosting this very interactive presentation that's going to talk about the NASA's James Webb Space Telescope, and we're going to learn about its mission and how it functions and things like that. So we would like to start off with a very fun icebreaker question just to get that chat going. And our question would be, if you are the person who is gonna have to lead that mission, what would you explore first? So where would you aim the Webb telescope to first? It could be like an object in space, it could be a constellation. Just write that in the chat. And while you're doing that, we are going to go over a quick Zoom tutorial. So just letting you know, this presentation is being recorded and closed captions are available. So you just have to click on that little CC button at the bottom, and then you can see a box that says show subtitles. When you click on that, you can actually change the font size any way you like. And then as you can see, we have the three boxes of our guest and our speaker kind of like obscuring our slideshow. So we recommend that you click on that gallery view and change it into speaker view. And then you go to view options, go all the way down to show subtitles. And then you can actually, I'm sorry, slide by slide mode. And then you can actually have your speaker box next to your slides. And you can adjust the width of the slides by moving the slide bar to the left and to the right. And then last but not least, we want to hear from you. We want to hear all your comments and all your questions. So please put them in the chat. And then, of course, we want to ask you to be good digital citizens. So just, be respectful to one another, but also to our speaker and to our moderator. And last but not least, I would like to introduce our very own astrophysicist, Dr. Rachel Smith. She is the head of the Astronomy and Astrophysics Research Lab at the North Carolina Museum of Natural Sciences. And she's also an associate professor at the Department of Physics and Astronomy at Appalachian State University. So she's very busy, and we're so happy that she can join us because she's gonna introduce our guest speaker. So let me stop sharing so she can do that. Hi, Rachel. How you doing?
Hi, Nancy. I'm well. Hi, everybody. So welcome to the last afternoon of Astronomy Days. I'm excited to be here, and I'm excited for our special guest, Dr. Carter Emmart. He is a good friend. I've known you, Carter, for 100 years or so, I suppose. And he is from the American Museum of Natural History. We go back a long time. And I'll just start by saying that we are, Carter is one of the leads on this software that you're going to see called OpenSpace. And we are partners with the American Museum of Natural History to develop visuals and programs with OpenSpace. And it is free. You can download it. We'll put the link in the chat. And Carter is one of the greatest storytellers I know and drivers of open space. And he's going to show you one part of it, but it really flies you through the whole universe. And so it's been a really exciting project. It's funded by NASA and we love it. And just a little bit more about Carter. He is the director of astrovisualization at the American Museum of Natural History in New York. So you may have heard of the Hayden Planetarium. He directs all those amazing space shows that you may have heard about. And he is quite an innovative director of visual media. He's been there since 1998, and they have many award-winning presentations and space shows that they've given that Carter's been involved with. And let's see what else he has. He has a PhD from Sweden's Linköping University, and he's won innovation awards, and you can read all about him online, of all of his awards on space visualization and astrovisualization. He worked at NASA Ames, a research center out in California, and also the National Center for Atmospheric Research. So he has a really solid science background that he brings into all of his work with OpenSpace and the museum. And he's had previous careers. Carter is an artist too, an amazing artist. He's was an architectural model builder and technical illustrator of space mission design studies. And he was the co-founder of the Case for Mars conferences. There are several conferences. Case for Mars conferences, which later became the Mars Society, which thinks about terraforming Mars. And I know he's not going to talk about that today, but that's just really cool. So without further ado, we'll welcome Carter virtually, and he has been to the museum in person too, so hopefully next time. So thank you, Carter, for coming and taking the time to do this for us. And I'll now give you the virtual floor for your talk.
Well, thank you, Rachel. I've been looking forward to showing you all this today. To show you, you've probably seen movies of how James Webb unfolds, but what I'm going to do now, I'll share our screen here. Can you all see that?
Mm-hmm.
Great. And so I'm going to just start off. Here's the, of course, the full package once it was delivered into space, all folded up. And we see sort of behind it is the blue of the Earth. And what I'm going to do here is hit the go button. And we're just going to quickly see this hopefully unfold. And we're moving away from Earth. And so we're doing a time lapse here. And you see that line? That line is actually the orbit of the Hubble Space Telescope, of which James Webb is kind of a replacement for. It's bigger and better in certain ways. I'm slowing down because right now we see the solar panel unfolding, and all of these items you're about to see that are unfolding are critical. We're going to move away rather quickly here, and it's going to pause again for a second. One orbit of the Hubble Space Telescope that we see down below takes an hour and a half. There's a tiny little thing at the bottom, which is a communication antenna that deploys, and then we're going to pick up speed again here. And that other line we see is the line of lunar orbit. And as we pass it 3 days after launch, finally the front pallet containing the sunshade unfolds. And there are 2 pallets. And so just as the Apollo astronauts took about 3 days to get to the moon, so did the James Webb Space Telescope on its way out to L2, which is where it's going to be stationed. I'll talk a little bit about that later. The aft pallet unfolds, and then if I swing around here, the next thing that comes down is a momentum stabilizer that we'll see. Oh, actually, what's happening is an extension. It's called the tower extraction, where you see the telescope sort of glides up and away from the sunshade a bit for the full deployment. And then finally, we'll see here this panel that unfolds. The telescope is large enough with its sunshade to actually be affected by the pressure of sunlight. And it's because the telescope has to be focused on one particular part of the sky and do long exposures. They have to account for any sort of momentum that's imparted by basically sunlight. And so this momentum flap is deployed off the back to sort of counteract some of that. Now, we come in closer, we'll see these mid booms that extract, and they are pulling out the 5 layers of sunshade. All of this, of course, went off without a hitch, thank goodness. And so we had 2 mid booms. All of this happens very slowly. If we look back, we can just see back on Earth. I use my pointer. We can see Earth down there, and one orbit of again of the Hubble Space Telescope takes about 90 minutes. And so with all of the sunshades deployed and then tensioned, we have basically almost a 500-degree temperature difference between the illuminated side in the sun and the side that's shaded. What's happening here is a very crucial step of deploying the secondary mirror. So all of this light that is gathered by this large mirror, which is 3 times the size of the Hubble mirror, and it's segmented into these hexagons, will all be focused on that secondary, and the secondary throws the light back down into that black cone that we see where all the instruments are, and the light is divided up. Now, the 2 wings of the mirror segments are finally completed and rotated into place. There is also, I didn't mention it, but off the back, there's a radiator panel that's deployed to get rid of some of the waste heat of just the electronics of the mission. So here we'll see finally the starboard side mirrors coming together. And if we just align along this, you can kind of see the parabolic shape that the mirrors maintain. And also right now they're doing this fine tuning of each individual mirror segment to get the focus precise and correct. That's why the first images aren't going to be available until this summer or late spring. So with this, we're out here, and I just thought I'd say a little bit about this place where it's going, called L2. So I'm going to pull away from the telescope. And in fact, what I'm going to do, let's see. I'm going to also turn on, we can see some other lines. These are lines of, they're trails of the orbits of the planets, blue for Earth, and we can see Venus and Mercury that are interior to our orbit, closer to the sun. And if I pull away from the JWST here, we'll see a label for it. Just a second. There we go. And also, I'm going to turn on the trail for it. It left the Earth and it cruised past the moon, but it's going 4 times the distance of the moon. It takes a month to get there. So here we see it cruising on out. And just this past week, they actually did a successful rocket burn to actually slow it down, to put it into this orbit of where it's going. So let me bring that up. There's a line, but I'm going to just discuss these sort of gravitational balance points between the Earth and the sun. So we have one between the sun and the Earth. We call that L1, and then L2, Lagrangian point 2, is out beyond the Earth. And once again, it's about 4 times the distance of the moon. And so let me actually, I'll get rid of the large points in the line, and I just want to speed time up here. So I'm going to race time ahead here. Let's see. Let me go to, that's, okay, this is about a day per second. Let's go 1 week per second. So what happens is we get out and we start to draw the trail with respect to the Lagrangian point, L2, where it's going. And so what it does is it sort of orbits that point in space. But as it does that, of course, it's in line with the sun. So if I come around to like this aspect here, and we see the sun seeming to course across the sky, and the sun goes through the various zodiacal constellations. It's going through Taurus right there above Orion. And so we can see that it traces out this sort of orbital motion around this point. So let me stop this now. And I'm just going to bring time back to about where it is now. So let me do that. I have to set a time clock here. Just give me a sec. Oh. All right. Good. And so this is before I went into time lapse, this is sort of where we started. So I'm going to come back down to the JWST. And there it is. And so what we've done is we sort of have a light, sort of have this somewhat illuminated just because of where it sits. Whoa, I didn't want that. I want to stop the time again. It's getting a little away from me here. Back down to, okay, that's good. All right. So here's the telescope. I mentioned that it has this parabolic mirror and to focus the light. So if we can think of aiming the telescope, let's look at what that would look like. And so I have these sort of parallel rays that go off to a vanishing point where it's observing. There's also a bit of sort of a light gray that we're seeing, which shows you the safety area. So in other words, everything in the light gray can be observed by the telescope, but it cannot point anywhere near the sun. And also, if it tips too far to look outbound, it would also, light would come in sort of the backside. So there's this band in the sky that that the telescope can see, and that moves along as basically as time moves along, because we go around the sun, as you just saw. That this band will also move across the sky. So they have to schedule observations for anything that you want to see. The astronomers who have written proposals for that, you have to obey this sort of stricture of at what time these observations can be made across the year, essentially. So let me just pull back a little bit, and I want to now show that if we just look across the sky, I want to call our attention to the beautiful Milky Way that, of course, our galaxy, and it's our home. And so even though I'm sort of looking toward the sun right now, and we see the galaxy, this is how we would see the galaxy with our eyes. And so this is the visible part of the spectrum. This telescope is actually really designed to look in the infrared. And one of the reasons for that is that with this large mirror, it's really going to be doing some amazing cosmological observations and accentuating essentially the deepest view we've ever had of the universe, with looking in the area where the Hubble looked in the famous Hubble Deep Field. I'm going to talk a little bit more about that in just a second. But because light in an expanding universe is shifted more and more toward the red, that those observations of the very far, very dim, that's the large mirror, and very, very far back in time because of just the light travel time. The sun, for example, is 8 minutes away from us, and the nearest star receive light from it 4 years in the past. That's why it's tuned to look in infrared. Well, what would the sky look like? What would the Milky Way look like with infrared eyes? What I've just brought up is an all-sky image of the 2-micron all-sky survey, and this is the near infrared, and you can see how the Milky Way looks a little different. We're in fact sort of seeing through some of those parts that were dark, and those parts that are dark are really visible light blocking dust clouds. But here in infrared, they actually glow. And you also see that there are a lot of stars that are not familiar to us because they're blazing out in the infrared that we just don't see with our eyes. So this is the 2-micron all-sky survey, but there was another survey done called the Wide Field Infrared Survey Explorer, and this is WISE for short. And so in this mission, we see deeper into the infrared, and notice how the Milky Way that becomes almost like a line, glowing here in sort of blue. It's been colorized. Again, these are invisible colors, so we've assigned colors to within the range of the infrared, sort of compress the blue to the red range here. But you can still see some of these dust clouds above and below the Milky Way, and they're sort of singing out in infrared light. And if we turn ourselves around and look outbound away from the center of the galaxy, which is where it's nice and bright, we look out just below the telescope now, we see clouds associated with the starburst region of Orion. And so this is what the sky looks like, not to our eyes, but to the sensitivities of the James Webb telescope. So let me now just bring this back to visible. And so this is sort of a little more familiar, and we see some of the familiar constellations. Let me turn it around about like so. There's Orion, for example. And so let's now turn on the constellations that we all know and love. And so here we see Orion in blue, and behind the telescope is Taurus the Bull. It's sort of a V shape, which is the face of the bull and the long horns, and the Pleiades. I'll put them just above the telescope. The Seven Sisters are the heart of Taurus the Bull. Now, astronomers carve the sky up essentially into real estate. And what I mean by that is if I just turn this on, we'll see these are constellation boundaries. And so if you read about, some observation and they found something, say, in Aries, there's constellation Aries. Aries is supposed to be a ram. It's about 4 stars here, kind of making a line. Doesn't look like a ram to me. But anyway, that if you find something in this constellation, you're going to call it Ari, the first 3 letters. And if you find something in Taurus, it'll be TAU, or in Orion, ORI. So this is just the sort of classification scheme. I'm going to use this now to point out one of the greatest observations ever made was in Fornax, right here behind the telescope, and the Hubble Deep Field. Now, they chose a part of the sky. In fact, it's kind of hard to tell here, but there are not many stars. And they had looked with ground-based telescopes and didn't see anything. And so what they famously did was aim the telescope at this sort of bare spot in the sky. And I'm now going to pull it around, and right there. So now let's zoom in. We'll see the telescope looking at where the Hubble looked. Now, this is just computer graphics. The telescope is finally real. It's there. But it's not doing any observations just yet. They're just getting it ready to do. So everything I'm going to show you, of course, is based on imagery that we have available that we will be looking at and making great discoveries with. So let's now look at the Hubble Deep Field. I'm going to turn this on so that we can see. All right. Yay. Okay, so there, what I've just brought up is basically a way that we can zoom in on this part of sky and see what the Hubble saw. So what I'm doing is I have basically a zoom window where the telescope is looking. And if I zoom in to where this little square just becomes like a crosshair right there, that's about the size of our full moon. And now let's look down below. So it's smaller than the full moon. And we see this is the famous Hubble Deep Field. Once again, surrounding it are observations made from the Schmidt telescope on Mount Palomar that gives us a view of the entire sky. But we've superposed over this in this inset. You can see sort of a diamond shape here is the Hubble Deep Field. Now, what's so amazing about this is that, once again, they chose a place that had hardly any stars, and we didn't see anything there. But after exposing about 200 hours with the Hubble telescope, and we can make this a little bigger for us, you can see everything in here is a galaxy. And so that's a star, actually. That's, if you see kind of something that looks has a cross on it, that's because of the diffraction from the telescope and the mount that holds the secondary and stuff like this. But that's a star. But everything else is a galaxy. And I can zoom in and we can look around. And what's extraordinary about this is that this is just one part of the sky, smaller than the full moon. But it's indicative of what we would see across the entire sky if we just had enough time and enough telescopes to look at, say, the entire sky. But you're seeing every one of these things is a galaxy. These are some of the farthest galaxies we've ever seen, because they had to collect that light over 200 hours. And we're seeing these very dim galaxies, very dim because they're very far. And so the point of the James Webb is they're going to be looking at the same field. They will see the same objects, but they will see many more beyond that. And they're hoping to see so far back in time, essentially, to the first stars, when the first stars are forming. So what we see are galaxies, but the galaxies, of course, are the integrated light of literally, in our case, our Milky Way galaxy has 200 to 300 billion stars. And so, you see our galaxy, would look something like this, if we were to just look at the whole set here. And then the smaller they are, the farther and dimmer they are. Okay, so that's one of the objects that they're going to be looking at. Let me go to another one. Let me pull back just a little bit and from here. And I want to, let's go now to the Crab Nebula. We're going to point where that is. And the Crab Nebula is just between the horns of Taurus the Bull. And so let me just call that up on the Hubble search here. So I'm going to be looking for a Hubble Space Telescope image. And that will take a second to load. And let me just let me manually, let's see, there we go. Boom. And this this is the remnant of a star that in 1054 there are records of this, of seeing basically a bright star appeared in the sky right there. That was a supernova, and it went off, and it created this nebula around where the star was, and there's a stellar corpse or a remnant of the star as a pulsar, which was the core of the star that collapsed and is extremely dense. And it's called a pulsar because it rotates about 11 times a second, I believe. And so we can actually pick up radio signals from this, these little beepers out there. It's like going 11 times a second. And that we could see the remnant of this. And so this is the end life cycle of stars. This is of interest. Let's also look at another type of activity region. I'm going to now search for something called Messier 82. And so we're going to look toward that, and I'm going to aim the telescope. The telescope went out of the view, but we'll move it around. You'll see there it is. And so what's happening here is just off the Big Dipper. If you have a backyard telescope, you can say, here's the Big Dipper. And you look up, here are the pointer stars that point out to Polaris and North Star. But just up here, there's M82. It's a pretty amazing galaxy, and it's also just next to another galaxy called M81. So if I bring this up, you can see here is this beautiful spiral galaxy, and it's been interacting with and perhaps causing what we see of this sort of chaos of what's going on in this active galaxy nuclei here in M82. This is a combined image. That the blue that we see in here is X-ray from the Chandra Observatory, which went up and just looks at X-ray. So we can see this is a highly active region. This is very hot gas associated with the core of this galaxy and starburst features. We get these things called starbursts when we happen to have like a lot of dynamics within a galaxy, and you have colliding gas clouds. And what happens is that pressure of these collisional areas creates stars and tremendous amounts of star forming. So we call this these starburst features that we see. Let's see, how are we doing for time?
Oh, you're doing just fine. Yes, we have about probably like 20 more minutes. And,
great.
And I have to say, everybody's like, wow, this is just mind blowing, right? That you can just point to something and then you can, kind of like enlarge and kind of zoom in a little bit. And so one of the questions was like, how come, is there something that you do that you can see these stars so big?
Well, it's what we're doing here is we're utilizing another software, which I want to promote here, because you can view it just in your browser. OpenSpace, you can download from openspaceproject.com. And we have a Mac build and a Windows build, and you can compile it yourself if you're a Linux person. But we are actually embedding something called Worldwide Telescope by the American Astronomical Society. And they maintain this software. It was originally developed by my friend Jonathan Fay at Microsoft Research. And but then it was sort of given over to the American Astronomical Society, and it allows you to zoom in and see all these wonderful features. Right now, I just zoomed in. I'm not sure if you noticed, but I brought it over toward the end of the handle of the Big Dipper. You look down here is the famous Whirlpool galaxy, and it's a beauty. It's about 35 million light years away, and about half the distance to the galaxies that we see in Virgo. So we call it the Virgo cluster, and that's a near a sort of big cluster to us of galaxies. But in this way, you can move around the sky and see these different features. So if, once again, I sort of zoom out here, and then I can kind of see where I'm looking. There's another galaxy up here called M101. I'll zoom in on that one. And but Worldwide Telescope is a fantastic ability to sort of look across the entire sky. What we wanted to do was put it in context to the James Webb, and we can also do this with the Hubble too. We can see, you know, look around the sky at these different features. So let's show you another one, and that I just want to pan back down to the telescope. We panned away from it a little bit, and remember I was showing you the center of the galaxy a little while ago, and so this is this region where the Milky Way gets really bright. And if I was to use my pointer again, we can see actually Sagittarius and Scorpius. So I'll put the telescope right between them. And so once again, these lines that we see here are kind of the racetrack trails of the planets. So they basically draw out the zodiacal constellations. It's where the sun goes through. So we have Scorpius, here's Libra, here's Sagittarius and Capricorn. I'm a Capricorn, so the sun goes through there in January. And what I'm going to do is get rid of those trails, because we have too many things on screen all at once. But right here, I'll trace out the Scorpion, and it has the red star of Antares, its heart, and then it comes down to Shala and Lasut. This is the stinger, these two little stars, the stinger of the Scorpion. And then Sagittarius, and Sagittarius is a centaur, and he's holding a big sort of bow and arrow, but it's more easily seen as this sort of teapot shape of stars, and so we call that the Sagittarius teapot. But right off the teapot spout, we see bright clouds of stars. It's really not a glowing gas, but this is this is the glow of starlight, and once again, it's being blocked by dust, so it blocks the light visibly. And so we were looking at that infrared. But I want to show you an observation of a starburst region called the Trifid Nebula. And so we're going to go to the Trifid here. We're going to aim it, and now I'm going to select that in Worldwide Telescope. And just give it a moment. It's going to load some of these for us.
Well, while you're loading,
question.
Yes, we do have a question, actually, if you don't mind. We
Please.
have Tyler who asks, like, why did we choose that position? Why did we choose L2 and not like L4 or L5? Is there
Well,
like
L4, no, it's a really good question. L4 and 5 are far away. L1 is we're on the illuminated side of the Earth, and so the Earth would actually be big and bright in the sky. At L2, we're on the night side of Earth, and so the sun and the Earth, and the Earth is warm, and so this is an infrared light is we're looking essentially at the signature of heat and warmth, and so we want the sun and the Earth, you know, in the same part of the sky, always on the other side of the sunshade. And but that's primarily why, and it's also close enough for us to have communications with it pretty easily, good bandwidth. Yeah. So let me I'm trying to load some of these other images. Is that not, that one didn't load? Let's see, let me try another one here. Okay, that's the one I wanted. Now, The red image is from the sort of general entire coverage of the entire sky. But as we look at this is an observation made from the Gemini telescope. And so I'm going to zoom in on that. And what we see in the heart of the starburst region is are blue stars. And blue stars are massive stars and very bright. They don't tend to live very long because they'll run through their fuel quicker. A dim star like our sun, we have it to thank for its longevity, its size. And so we're about 5 billion years of burning so far. The sun, so it's about 5 billion years old. It's got another 5 billion years of gas to go. It's getting a little brighter. So that has effect, of course, on us here on Earth, like about 100 million years or so. It might be a little warm here. But what I want to show now is I'm going to bring a couple images together. This is what a starburst region looks like in this infrared. And so if I come in here, it looks somewhat different, and we don't see this main feature that we were just seeing. In fact, let me just do this there. So the silhouette, once again, is dust that's sort of blocking our view. But with infrared, we can look through that dust like this, and then we see the stars, sort of a clear view straight into it. And also, I think there's one other image which is really quite nice. Let me see if I can find it. That's the close-up. Okay. Let me see if I zoom right into that. Oh, I have to really fade this one down. There it is. So that's this is a Hubble image. I'll come in close. Right here, this is the Gemini image from Hawaii. And but as I fade that down, we'll now see this image here from the Hubble Space Telescope, where we can see details just because in space we don't have any atmosphere to worry about, and so that we can really focus the image. And that was the purpose of the Hubble Space Telescope in seeing so much more than we could actually see from the ground. And so those pictures are legendary. And the James Webb will see with about the same resolution, but with tremendous light gathering capability. So what I just thought what I'd like to do is see if any of you, have any more questions, but also if you have any favorite objects you might like to see, and then we can try to look for them.
Yeah, we have a few people who kind of like have requests, and we also have just one question that popped up, and it's from Scott, and wanted to know, what are the first set of observations that we hope to see from a James Webb telescope, and when will it become available and operational?
Well, it's the first image is due to it's going to be a highly celebrated press release and all this, but we're expecting probably late spring, early summer.
Oh.
And I think I've asked this question to my colleagues, and nobody knows, because I think they're keeping it a secret where they're going to aim it, and to have a really great image release. So I wish I could tell you, oh, it's going to be this, that, or the other. But
yeah,
it kind of makes it
like, well, can you put it on the map, right? But that's not possible because you don't know. We don't know it. Yes.
Well, they will target something, a great image. Do you remember the pillars of creation, the M16? I'll look. Let's look that one up. The Eagle Nebula. And this one, I didn't have an aim point for the. I didn't have an aim point for the telescope, but so I won't be aiming the James Webb in this, but I can with Worldwide Telescope. Look, and here we see, here's the teapot, here's the scorpion, and just above that in Serpens, and I'll just move the sky a little bit here, and then we can see the star Altair. It's part of the Summer Triangle, but in a backyard telescope, you can see that what's called the Eagle Nebula. And it kind of has this kind of almost eagle shape. So we'll bring this up a little bigger. And here we see kind of the head of the eagle, the talons and the wings, and very nice. And but let's zoom in on that. And let's see, this is one of the most famous Hubble pictures called the Pillars of Creation. And there we see how much more resolution that the Hubble could see. And once again, the James Webb is 3 times the mirror size of the Hubble. And let's zoom in here. What we see are these interesting little features. And these are dense parts of this gas cloud that are surrounding young stars that are actually forming. And what you also have, here's one that's encapsulated. And so we can see that this is gas and dust that's surrounding basically a young star in birth. Now you say, what's all this? It looks like it's evaporating away. Well, remember I said there are blue bright stars, and blue bright stars are, there's probably some blue bright stars behind this. And here's one. And what they're doing is because they're so bright and they have a very fast stellar wind, they actually sort of start to sculpt the nebula that they were born from and blow away basically the gas and the dust. And so what it has an effect of making it look like it's essentially sort of evaporating away. This is the ionized gas region. So it's actually it's illuminated from the star. It's also singing out in its own frequencies, but also these dense star regions are around this. And so this is an amazing picture when you consider sort of the resolution of what we have from the ground.
Yeah, so and this is exactly what Keenan was asking for. So
great. Okay.
I put it that way, yes. And then we also had a question from Jasper. Could you potentially look at exoplanets?
Oh yes, in fact, let me. That's a very good question.
And he was asking the same thing to a tour of a few of the exoplanets.
Okay, so with the exoplanets, it's usually a kind of a different program to talk about. Now, a large part of the mission of this telescope is to do spectroscopy. And so spectroscopy allows us to really look at look at an object and get a very detailed readout of its spectral range. And whereas it's not going to really see much more than we have seen of these exoplanets, where there's the light of the planets is being reflected from the host star. We've seen that with other missions, and we will be seeing that as well with the James Webb. But the important part is the spectroscopy that is going to be doing. And so when stars eclipse, when exoplanets eclipse their host star, and just that little thin atmosphere, like Earth, our atmosphere is about as thin as a skin on an apple if you scale the Earth down. But just that moment where the starlight is being eclipsed by the atmosphere as the planet moves in front, will give us basically a profile of the spectrum, and it will tell us the chemical signature. So we'll see what the chemistry of these atmospheres are. Mm-hmm. And so if there is anything that is similar to what we have here on Earth, it could be a signature of life itself. And so that's very exciting. But let's just look for a second. I'll bring up for us here the exoplanets, a map of where we see where they are. Mm-hmm. And so we do that. And what I've done is right here, we see blue circles. If they're smaller, they're farther away. And so the telescope component, I'll minimize that because that's not so much what's important here right now, is that we're just looking that across the sky, we see these are locations of where we have exoplanets. And if you'll notice, all of a sudden we see a whole bunch right up here. I had pointed out one of the stars in the summer triangles called Altair. It's about 16 light years away. And then we have Vega, which is 20 light years away, in Lyra, or the Lyre. So this is the goddess's harp. And down here, Aquila the eagle. And then up here is Cygnus the swan. Some people call it the Northern Cross because it has this fairly prominent set of wings. And then here's the tail of the swan called Deneb. So this makes up the summer triangle: Deneb, Vega, and Altair. This star is 2,000 light years away. And it's almost as bright as like Altair, which is 16 light years away. So this is an extremely bright star, and it's very far away. Between Vega here and Deneb is this area that was targeted by the Kepler mission. And in that case, they were looking just in one part of the sky, and they were waiting for these planets to potentially go in front of their host stars. And so we see like almost about 2,000 of them there. It's amazing. So once again, like the Hubble Deep Field, remember, we're just looking at one little patch of sky, and there's a lot that tells us. What this tells us is that planets are the norm, and that perhaps all stars have planets. We also know that, remember I was talking about the Milky Way galaxy, that the Milky Way galaxy is, we know we have about 200 to 300 billion stars. So in our one galaxy alone, if you remember, you saw all those galaxies in the Hubble Deep Field, that a typical galaxy like ours may have, in fact, about a trillion planets. And we're the only place that we know of that has life. But anyway, it's vast. So are there any other questions?
Yes, actually, we have one question, and it's more about the James Webb Telescope. What is the life expectancy of this telescope?
What is the
life expectancy? Like how long?
How long? Yes, in fact, I should have mentioned this, and so thank you for asking this question. Is that its life expectancy? They were hoping it might be about 10 years.
Okay.
But the thing is that is reliant on how much fuel it has, because every now and then it has to make a little burn to just maintain that orbit at L2. They were very efficient. They were right on the money when they launched this thing. So we ended up with more fuel than expected. And so its life expectancy will go beyond 10 years if all goes well. And then there are even ideas of sending a robotic spacecraft out to it with more fuel to even boost it in the future. So I think the jury is out on how long the telescope will last. That's a really good question.
Yeah, because I mean, Art just pointed out that Hubble lasted decades, so maybe this one has more life in it than, initially.
Yes.
Because one of the questions that I would have is like, couldn't they harvest sunlight instead of like the fuel to adjust and keep it in its position?
Well, that's so we can use sunlight, and we are with what powers it are the solar panels, and the solar panels are this right here, and also there's some ancillary solar panels here as well. This is the communication antenna. Let's see if I can get in. I sort of only get so close. But in gold, we see the communication antenna, and then we see the solar panels, and we see the little rocket engines, the fuel, and also we also see there are star trackers over here that allow them to basically, they're doing an observation, but they within the autonomy of the system, they can basically hold the position on those stars, and so it's a separate system from the data taking on the other side, which the mirrors. And, as I mentioned, the light is focused into that sort of dark cone that's in the middle, of the whole array of mirrors, and that's where the light is then divided up into the multiple instruments. All told, I believe about 22 nations from the European Space Agency. We have Canada and NASA. So all told, I think it's about 24 nations all working together on this. I've just aimed it in between Chiliac and Sulafat. These are two stars in Lyra in the summer constellation. And some of you may know that just between those two is something called the Ring Nebula. So I'll just bring up the ring for a second. Oh, here we go. And so we'll look at that. And so some of you may have seen this in your backyard telescope. They're called planetary nebulas because they're about the size of, you would see, Jupiter. But to the naked eye, it's sort of dim. This is a nice Hubble picture where you can see lots of detail. But let me show you another picture with infrared. And with infrared, we get a view of some of the outer envelopes of this star. So this is a star that went nova, but not supernova. So it blew off its outer atmosphere, but not quite like we see with the Crab Nebula, which was a more powerful star, a brighter star that blew up. So are there any, does anybody have a target?
We actually have probably time for one more spot. And sure. The Rhonda was asking, could we please look at the secondary mirror?
The secondary mirror. Okay, yes, let's do that. Let's come in close. And the secondary mirror, I can only get in so close, but we'll see it. And then I'm gonna just try to guide us in here as close as I can to see it. And that secondary mirror is actually parabolic as well. Let me move our Ring Nebula to the side. And so you have this, the primary mirror, lower left, and it's going to focus all that light. You see the sort of parallel rays going off to the target, and they get focused right up to the head of this tripod. So the secondary is right in here, and then all that light combined goes like a needle point straight into here, and where that light is analyzed and where the images, the imagers and spectrometers are.
Yeah, Jay was asking how big is a secondary mirror? Do you have a guess?
Oh, well, I think each one of these mirrors is, so this is about 6.5 meters across. These mirrors are large. I saw some of them when they were constructing the telescope at NASA Goddard. I didn't see the whole thing really completed. I sort of saw it through a back door. We were getting a tour, but when I had been up in the gallery looking down, we saw those mirrors. So if you look at look at the mirror here, yeah, it's about. Well, I actually have an image that I might be able to share. This is just from a Google search. Let me just show it to you, but it shows a person for scale. So I'm going to just quickly change my share. So we'll see that. So can you see here's a person, yeah. And we can see how small the Hubble mirror is by comparison. And so the secondary, I think, is probably about 3 or 4 feet across. It's pretty respectable. So I'll go back to sharing open space again. But again, you can download open space. We have the Webb telescope in it. What we don't have is we're going to be bringing out in a later version this what we call the sky browser with Worldwide Telescope. But if you want, you can search the sky already with Worldwide Telescope. Just look them up. Once again, it's the American Astronomical Society. But you just search for it for Worldwide Telescope. In open space, you can get the Open Space Project, oneword.com.
That's excellent. Thank you so much. I mean, there are a few more requests, but we're unfortunately running out of time. I think I could do this like all day long.
Can I show you one?
Yeah, sure, of course.
Okay, let's look at a horse head. Here we go, and So it's going to pan us around, and I sort of lose the telescope. But this one's just so nice. And it's also in Orion. And here's the horse head. It's kind of upside down. I want to flip him around like this. There we go. And so the Great Nebula of Orion is just below the belt, but right here is the beautiful horse head, and this is one of the stars of the belt. And so there we see the belt of Orion. So let's zoom in. And once again, with visible light, this is what we see. We see the horse's head. I'll make this bigger. And but if we look at this with infrared light, let's do that. Oh, hold on.
Yeah, Scott, there we go. I appreciate seeing the greatest hits of astronomy during this talk.
Yeah, it's kind of fun because it is a telescope that's going to be doing this. And but I want to show you one cute little thing about this. So with infrared light, we don't see the gas. We see through the gas, but we see the dust. And but I wanted to, from this Hubble image, zoom in right to the edge of the gas. Can you see this? That's a galaxy. And so we're zoomed in, and just like the Hubble Deep Field, there are all these galaxies, and these are more galaxies, more galaxies. So wherever we look, we see galaxies that are
endless,
as easily as big as ours. Once again, hundreds of billions of stars, and possibly trillions of exoplanets. And but just I love this picture because you zoom in on, you sort of have this wonderful sort of negative view of the horse head. Once again, I just fade this down. So that's what we see visibly, and then that's what we see in infrared. And then you zoom in on these images and you see galaxies. You'll even see through galaxies to other galaxies. It's the Hubble is a staggering a staggering instrument, a great legacy, and the James Webb is just going to make it so much more. Mm-hmm. And so this is so exciting to be alive at this time and be able to then that the telescope got there, it's deployed all its parts, and we're now waiting for the engineers to get it ready so that we can see all that it has to show us. Thank you.
Yes, and go ahead.
Oh, sorry. No, Nancy, before we go, I just want to remind everyone, there's a survey for an evaluation for this talk because of the software being in development. So if you could please fill that out, those of you who are watching, and I think they're going to put it on the YouTube version too, that would be helpful. This helps the developers see our programs and see how they're going. So it's very helpful. Thanks. I just want to mention that. And Carter, this was awesome as always.
I zoomed in on the Orion Nebula, one of my personal favorites.
That is one of my favorites too.
That's awesome. And Art just posted the survey link in the chat as well. So you can just click on that and take care of that. So thank you so much. So with this, we're going to have to unfortunately end this program because I know that there's another one at 3:30. It's about the Fermi paradox, why ET can't phone home. And I'm sure a lot of people want to go to that one as well. But I want to thank you, Dr. Carter, for being with us today. This was just wonderful. I really enjoyed this, and everybody else enjoyed it as well. And I want to thank the North Carolina Space Grant and Pepsi, like our sponsors, and of course our loyal museum members, because without their sponsorship, these kinds of special events wouldn't be possible. So thank you, and please consider becoming a member as well. And then if you do that, you might actually also get a 10% off of our astronomy t-shirt, which is really cool as well. And then last but not least, thank you all for coming, and I hope to see you with the next program. Y'all have a good day. Thanks. Bye.
Thank you, Carter.
Thank you. That was fun.